Yeah.
C++.
No, I'm going to start with the C++, just to show them the harder one.
I showed how hard it is to do in Verilog.
Yeah.
I already did the hard one.
Once you guys see the Python, you'll be like, what?
Okay. You have the microphone.
Yeah.
Okay.
Or if you want to see the Python, because you're standing for a little bit, I can show the Python first.
Yeah. Show Python first, or I should show one of the general basics first. That's what he did after Monty Python did a bunch of corporate training videos.
Really? I didn't know that.
Meetings, play meetings. And it talks about how the whole point is how to run effective meetings in a corporation.
Oh, man. That's got to be great. I haven't seen that. Let's see. All right, guys, let's start. So I don't know if you guys remember this. This was like week 2 or 3. I did a simple like ISA design assembly demo where we were just summing up things in an array. So this was that C++ code where we had an array and we were summing things up and just storing back. So this was the assembly code for that. So we had a loop, and then we had an end loop. So in the loop, we're getting our loop limit, essentially, of 40, and then we're doing our set less than, just checking to see that the loop counter is less than 40, and then loading in 7, because 7 was here because if it's greater than or equal to 40, we want to break out and go to end loop. So that's what I store that into a R0 register, and that's what the branch NEZ does. It just checks all that stuff. And so what I did was I just copied that code, simple, basic stuff. It's the same code. We removed all the labels because before it was loop and end loop at the bottom. You don't need that stuff. So you can manually go in and remove that stuff from your code when you're doing your assembler, or you can make your assembler more smart and then take care of that. So the way to do that is generally you would have like loop, and you would have everything in that label like offset by a tab. So you can check to see if the first character is a tab, and if it's a tab, then you know that it's actual instructions. If it's not a tab, then you can just disregard that line. So that's one way to check. So you can add that intelligence to your assembler. But for the purpose of this example, I just removed it because this is a real simple, stupid one. So let me show you the code for Python. So in Python, I am using a library called bitstring. So what this library does, it just lets me get 2's comp from integer values, 2's comp binary representation. So I made 2 dictionaries. So a dictionary in Python is a lot like a hash map, sort of. So it functions in the same way. So I have 2 dictionaries. One dictionary is for opcode, and another is for registers. So for this example, I just had 8 instructions. And so on the left-hand side, we have our mnemonic for our instruction as a string. And on the right-hand side, I have the number like that represents the 3-bit opcode. So for this example, I just went with the 3-bit opcode. So 0 is 0, 0, 0, blah, 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 down to 7, 1, 1, 1. So that's what that means. So I'm going to be converting these to binary. I mean, I think you could have also done just written in a string, you know, just as like 1, 1, 1 instead of 7. That's also one way to do it, but just to show you guys ordering of it and make things easier and just show it in decimal format, I did it this way. Then you have registers. So I did the same thing with registers. I had 8 registers for this example. So you could have R accumulator be R0 or whatever. Some of you guys have dynamic accumulator registers where it's changing. So you can have that set in your assembler as well to keep track of that. Then let me show you guys the main statement, or the main method. So what I'm doing is I'm opening this file that I have, the one that has everything removed, no comments, just blank assembly. I'm opening that, and I'm opening to write a new file called machinecode.txt. So that's just going to create that file for me. And then what I'm doing is for each line in this file, I'm splitting up. So for each line in this file, I'm splitting up the words. So the words are like li would be one word and 32 would be another word. So I'm splitting those up. So that's what this Python function line.split does. It just takes each word in a line and makes an array out of it, essentially. It makes a list. And then what I'm doing is I'm calling assemble machine code function, which is this function up here. And I'm passing in that list of words in my output file. So let me show you what the function itself does. So the first thing I want to do is see the number of words in that sentence. Why do I want to check the number of words in the sentence? Because if I look at this, the number of words in a sentence tell me, in a sense, what kind of instruction type it is. So li32, that is like a load immediate. So I have an opcode and I have an immediate. But let's look at lbr2. So lbr2, those are still 2 words. And I have an opcode and I have a register. So that's totally different than this kind of 2. And I take care of that, and I'll show you guys that. But for the sake of this example, with just one word in a sentence, I just need to look at the opcode for that. With 2 things, I have 2 with 2 words in a sentence, I have 2 cases. One where I have an opcode and a register, and the other case being an opcode and an immediate. And then the third case is I have 3 words in a sentence, and the first one is an opcode, and the other 2 are registers. So going back to this, what did I change here? So for the first case where I just have an opcode, or just like I just have one word in the sentence, that's what this guy is, I extract what the word itself is. So what this does is that word 0 means the first item in the sentence. So what I do is I pass it to my hash map or my dictionary here for opcode. So it's passing it in for the first one, li. So it's going to go and look at li, and it's going to return 0. So li, or op over here, op is equal to 0. So what I need to do now is write 0 as 3 bits in binary format to my output text file. So that's what this guy does. Write, and then Python has this built in, so there's a couple of ways to do it. The library that I showed you at the beginning, that was only to handle twoSComp, but Python itself can also do integer to binary stuff. So what you can do is called format, and the first parameter is the integer value that you want to convert to binary, and then the second parameter is for binary, and then I want to fill, or this zfill tells me how many bits I want to show that value as. So I want to show 0 as 3 bits because my opcode is always 3 bits. And we know that from the range of opcode here that I'll never go over 8 items. So it'll always fit in 3 bits. Then to make a 9-bit instruction, what I want to do is just fill out the rest of it with all zeros. So what I do is I just pass in 0, I want it as binary, and I want it as 6 bits. So what that's going to do is just essentially give me all zeros for the first instruction. Yeah?
Just quick question. If let's say the way we do separating the type is not dependent on the...
No, it's not. Yeah.
We use opcode to separate the type, then how will we go about that?
So what you can do with that, so Python doesn't have a switch case. It has if-elses. So what you can do is, instead of having a dictionary like this, what you can do is have if-else and check each opcode. And so if you have a function, let's say the opcode of 001 has function bits for it, and the other ones don't. So when you see opcode equals 001, you're going to have another set of if-elses. Or if you do, in the C++ one that I'm going to show a little later, I do that. I have a switch case within a switch case. So that tells me that for the opcode that is equal to 001, I need to go look at the function bits. Then I have a case that handles each case of each function bit. And then, just for sanity's sake, I also add in comments to the assembly code of what that instruction was in my assembly. So you're not just looking at a bunch of zeros and ones when you're trying to debug your machine code. You can also write in comments what that instruction was. And then when you read it in from ModelSim, like with that read memb command, it won't read any of this. It'll just read the zeros and ones. So let's look at the case where we had 2 words in our sentence. So I want to do the same thing as before. I want to get the value, the decimal value of my opcode, and set it into op. And then I want to write that as binary 3 bits. So this is how I handle the case of if the second word is a register or an immediate. So I check if registers, so in Python for dictionaries, you can use the hasKey function. What this does is going to tell you if whatever item I'm trying to check in this dictionary, it'll tell me if it exists in there or not. So if I pass in anything that's not a register, so if we look at the registers, if I pass in anything that doesn't look like R0 through R7, it's going to return false. So that's how I handle immediate or register. So if it has it, I'm going to treat it as a register, and I'm going to get the value, and then do the same thing where I want to write it as a 3 bits binary for what that register is. And then also fill out the other 3 bits. So I could have switched this. So what you could do here now is, let's say you had a func code. What you could do is look at the, use those other 3 bits of the word or not, or the instruction or whatever, and figure out how to fill out what the function is. So this one was for if we had a 2 instruction or 2 where you have an opcode and a register, then you can also determine from what that opcode what you need to make its, from the mnemonic itself, what you need to make its function code be. And then if it wasn't in the register dictionary, I want to get the integer value of the immediate from the string. So this is just a string to integer conversion right here. And then this is one little hack I had to do where if I was trying to convert it using just the Python format to binary, it wasn't doing toScomp for me. So this is where I had to use that library, and this is what that function call is. So let's say if the value is positive, it should actually be greater than -1. So if the value is positive, I just want to write it as binary like we did before and use 6 bits for my binary. If it's not positive, I want to use that library call. So what the library call is, it's just this function where bits, and I want to pass in the negative value that I'm going to have, and then I want it to be 6 bits in length, and then the .bin just returns zeros and ones. It'll cut off the 0 apostrophe B, like the binary representation that you usually see. And then I want to convert that to a string and then write that to the output file. And then I do the same thing as before where in comments, I write out what the instruction was in assembly. And then the third one, if I have 3 words in my sentence, this is the easiest one where I have an opcode, a reg1, and a reg2. And then I do the same thing where I just get the value of what the op is in decimal, get reg1's value in decimal, and reg2, and I write all 3 of them as binary. So let me run this, and I'll show you guys how it works. Too small. So this is more like a Python script, that will just convert it for you. So like I said, it's going to create a file called machinecode.txt. And then that's where all our machine code's going to be. So let's run this. So I just had little print statements that show me that it's assembling each line. Yeah, it's actually working. So let's open up the machine code that it just made, and voila, here we go. So load immediate, we had opcode as 0, so I got 3 bits for 0. And then 32 was my immediate that I wanted to load in. So that's the immediate 6 bits of 32. So it's working correctly. And then you can see in comments, just for checking for sanity, this really helped for me last quarter in Lab 4, was when I was referencing against machine code while I was doing model sim, it helped a lot to have the assembly instruction commented right next to it. So you see all these line numbers right here. Imagine just subtracting 1 from it, and then that's like your index, essentially. So when you're looking at a PC and you need to know what instruction it is, you can see what it is by just looking at this and so just subtracting 1 from this count. And that helps immensely when you're debugging branching, seeing what's going on with the instructions, where things are broken, et cetera.
So you're running models and you watch your PC, you can see the PC, you can see the table head, you know what's supposed to be there, you can track what's going on.
Yeah.
That's the key. If the program counter's not happy, you're not happy.
Oh yeah, that's like the first bug you encounter is incorrect branch distances or targets, because yeah, exactly. Yeah, so it might just get stuck in a loop, and just keep on running your code, and then you'll see like, wow, it's going to like 300,000 dynamic instruction count. That doesn't make any sense. Yeah. Yeah. So you'll be like, what's going on? And then you'll see like what range of instructions are being run, and you'll be like, yeah, this is not making any sense. So that's why this helps a lot. So that's the Python way. And you can see how much code this was. Let me just zoom out. Yeah, I'll post this one. I won't do the C++ one because that's the one that I did last quarter. But I learned Python this quarter, and look at it. 77 lines. I got just a basic version working, and it was very simple. If you look at the C++ one that I'm going to show you, it's a lot more code. There's a lot more things you have to handle. If you want to do the system Verilog way, more than welcome,
It's probably about as long as the Python.
Yeah.
So I think the C++, I think Python is still pretty good.
Oh yeah, like even this, like syntactically, Python, if you look at it in here.
God was designed for this sort of crap.
Yeah. Like 4 word in words. It doesn't get more simpler than that, So that's the cool thing about doing it this way. So let me show you the C++ way now. Bye. All right. So let me show you what my original code looked like. So this was my original code for problem 17, 18, 19. It was different than your guys's. So I had all this junk in here, It just goes on and on and on and on. So 171 lines, and I need to convert all this into machine code. So the first thing that I did was, what was really weird for me was I wanted to remove all these block comments up here. So that was the first thing to go. Let me open up that. Oh, no, I actually took care of the block comments. Okay, so the only thing that I really took out was the labels. So this was my original code. This is the one that my assembler is going to read. So I removed all the labels. I even left in my comments. So I removed all the labels, and then I made sure that my branching was okay. So I removed all the labels, removed the white space as much as I could. So what's happening is that there's there's a tab right here. So the first character of an instruction line that is an actual instruction has a tab for me over here. So I'm looking to see if the first character of a sentence or of a string that of each line that I'm reading in is a tab. If it's not a tab, then I know that it's not an instruction. Then I disregard it. So over here, we know that the first character is this thing. First character over here is actually a space, so on, so on, so on. So my assembler knows, like, junk all this stuff. I don't need it. So
You pass into your Python assembler script, you don't have to label it.
So this is my C++ one. I mean, you can have a label. It doesn't matter, but just have a way to differentiate between a label sentence and a sentence that has an instruction. So like if you do Spark or anything, they totally like you have your label and then next line you tab it, and then you write your code. You have a question? Yeah.
Does your assembler record, like let's say you're jumping or branching back to prompt 17 label, right?
Mm-hmm.
Does your assembler recognize which line it is, or like how many instructions?
Oh, so the way I handled branching was I explicitly counted and set the values. So, yeah, that's the even more smarter way to do it. Yeah, of course. So you can, like, when you hit a label, you can, like, have a value that stores its line count, Just be counting all the lines, and then be like, all right, this is the line count for this label, or I've hit a label. And then when you've actually hit the label that it was going to, you can record that count and then subtract the two, and that'll give you your branch for relative branch distance. If you're doing absolute, you can just look at where you want to go to and code that in. Yeah, I thought I didn't want to spend too much time into my assembler, so I was like, you know what, I'm just going to remove all this stuff, look at all the instructions, just format it nicely in a text editor, and then just use the line numbers right here to tell me what my distance is. And that saved a lot of time. Yeah.
So we're going to assume like each program starts from 0.
Yeah, exactly. Yeah, so I didn't know that last quarter, so all my instructions were in the IROM, so I had like 230 for all three of them. So I had to count like manually for like it's jumping here to here, this is where this one starts, But yeah, you guys can do it where each one starts at 0. Each one is its own thing. Yeah. So that helps a lot too. So let me show you guys actual code for this. So already off the bat, we have 194 for my main, and then I have another file parser that's like 363 lines, and then a header, 37 lines. So add that up. Python's way easier. So let me show you the parser, or the main. So what I'm doing here, I made it, let me show you how it runs. So just basic comments, I just made a make file to make the assembler itself, make clean. So this is how you run it. You do beth9 ASM, you pass in the assembly file that you want to convert from assembly to machine code, and then the third one is the name of the text file. So that's how it does it. So just to do all that, you have to do all that stuff of checking your argument count, checking your argvs, all that business, So it's more, this is what I was used to in C++. This is what you do in 100 and other courses, you check all that stuff. In 30, you do this with C. So just even opening a file and checking like how big it is and whatnot, it's already like 4 lines. If we look at the Python, where'd it go? This is opening a file. That's it. It's opening 2 files and then checking line count. It's way simpler to do certain things in Python. Their libraries are way too simple. So I opened the file. I want to check to see if there was some failure. I had all that code there, whatnot. So this is where I actually begin reading the assembly code. So while my file is good, I want to get the line. So, and store it back into or get the line from input. And then this is where I check. If the first character of that line is a tab, then I know to just delete that tab and remove it. So, and then I have a switch case. So this is where things got a little weird. So I do a switch case to see if the first character after the tab is anything other than these. So I had if it's a null character, a tab character, a space character, or a comment like /. So if it's any one of those, I don't do anything. But if it's anything else, then I know that it's an instruction. So what I do is I call this helper function called tokenized string, and that will basically break up my string. So that's that line dot split in literally. But if we look at tokenized string, I do all this junk here, where I want to remove certain things. So you can even do this using regex in Python. So using regex, like the convention when you're writing code for like MIPS or Spark is use like $R whatever, or even in ARM, that's how you write like a register. But let's say if you coded it that way, are you going to manually go remove each $, or each like parentheses or whatever, So let's say like in a load word or store word in MIPS, there's like you do load word on your target, comma, and then you do your offset, and then in parentheses you do your RS, your source register. So there's a lot of like syntax junk there that you don't need. You don't need the parentheses. You don't need random things. You just want to space things out. So that's what this did in C++. But in Python, regex can take care of that, where you only want to look at alphanumeric characters, and it'll just remove everything that's not alphanumeric. So let's go back here. So I basically split up my sentence. That's what this tokenized string does. And then I pass it to my parser and parse tokens. So let me show you my parser. So in my parser, I have a typedef enum. So in C++, you can't do a switch case on strings. It doesn't work. I don't know why. It's just a language construct thing. But you can do a switch case on typedef enums, and that works perfectly. So what I did was we had this typedef enum, and I called it instruction. So each one of these represents like the different instructions that I have. So I had a load word, clear, increment, all this stuff, and each one of those represents an instruction in my ISA. Go back up here. So I'm doing a switch case on that on a string. So if s is equal to something, so this is where I do my tokenized stuff and I pass it here, and it returns the enum. So each one of these corresponds to an index. So li is 0, clear is 1, so on and so on. So that's what it's happening here. So that's how I'm able to determine what instruction's being read. So if we look at my parse token, so I have a string stream parse token. This is just like building a sentence, essentially. A string stream object lets you just use like cout, or just use the same like cout, cin operators to write a sentence, and then whatever you want to do with that sentence, you can write that to a file. So I had 3 strings for different possible things going on. I can have immediate binary string for immediates, and I can have a register binary string for like if I just had one register operand, or if I needed a second register operand, I'd put it in register binary string 2. So this is where I do the switch case on my oh yeah, so one more thing to note is that everything that I have in, where is it? In tokenized string over here, I push it to a queue. So with a queue, that's first in, first out, and then I'm going to pop them off or front them and then look at it. So with the first in, first out, I'm guaranteeing myself, I'll just use that just to say that I'm going to look at the first like word in the sentence, then the second, then the third, and then the fourth. So what this does is was the reason I used a queue here, because for when you have a different types of instruction types, so if we look at the original code, so sometimes I have like 2 words in a sentence, 3 words in a sentence. I'm trying to see if I only, yeah, it was generally 2 or 3. I didn't have one where it was just like 1 word in a sentence. except for halt. Halt was the only one that was one word in a sentence for me. So with the queue, I know that when I front and if it returns a null, that I've hit the end of the queue. There's nothing else. So by knowing that, I'm able to determine different types of instruction formats. So this is how I do it, and then I just write, you have all this code, and then get bin from int and s2i. I had to create my own functions, do to's complement and all that stuff. I'm sure there's C++ libraries, but I just did it myself. Yeah, but you can do this in Python way easier, like I showed you. Just use the library off of GitHub that someone has to do conversions from integer to to's complement, You're more than free to go and do that. So I have all these switch cases, So a lot of the stuff is doing the same code, It's terrible, design practice. This is violating the dry rule, or I guess, you guys probably heard of that. This is just terrible, It's doing the same shit. So that's what the dictionaries in Python help a lot, is that you don't have to repeat all this code, You're just sending something to a dictionary, getting the value back from the hash map, and writing whatever it is after you convert it to binary. So that's where it helps a lot. And then another way you can abstract this even further is that for your different instruction formats, you're going to be doing the same thing for each format. So you can have a way to figure out what format it is by looking at your opcode, first thing, and then maybe have 3 functions or n number of functions for different types of format. And then that way it's going to do the same thing for each format, and it'll know what bits to look at in what position to determine registers, immediates, whatever. So that's the C++ one. And let me show you guys how it works. Make. There we go. ETH9 ASM. I want to pass in assembly file, and we'll call it P17 machine code. So it assembled that one. So this is really dumb too. I had to do it for each one, for each of the programs. You can probably have it do them all at once if you want. Make it even smarter than this. And then what I did was I just used cat P17, P18, P19. And then I want to just output that into machinecode.txt. I did that. And then if we look at machinecode.txt, it's not this folder. It's in here. Right here. So I always output at the beginning just the name of the file that I was converting from assembly to machine code. So you guys don't have to do this at all where you have to combine them, because you're starting from 0 for each one. That's why you see that at line 77, you see the beginning of P18 and then 107 P19. So for you guys can just do it one program at a time. And it does the same thing, but this was way more work in C++ compared to Python. And if you haven't used Python, it's real simple. You guys, CS people can pick it up in a day, System Verilog way, I recommend. If you really, really want to learn System Verilog, go for it, But, yeah. Don't do it that way. Yeah, that's all I have, guys. That's it for today. I was coming for Darren. You guys have any questions on assembler, approaches, anything like that? This lab's pretty straightforward. Make your assembler, and then code out the rest of your ISA. Do the whole top level. Doesn't have to run yet. That's what Lab 4 is for. But if you have everything done before then, just start debugging it, make it run, and then finish your quarter for this class, There's nothing else you have to do after that. Yes, you're going to have to turn in your assembler. It's Top levels for this lab also, yeah. Yep, that's it, guys.